The Cool-It Project by Caelan, 25th of November 2013. First we got a glass of water. Then we put a temperature probe into it. This temperature probe was hooked up to a calculator that was recording the information the probe sent to it. The probe recorded the temperature of the water after each minute. This went on for 45 minutes. The information was sent to the calculator, where the calculator graphed it on the screen. Here is my table. This table is slightly different than the data originally collected from the calculator. This table shows the temperatures after every 5 minutes, starting at 0, then 1, and then skipping every 5. On the real information table, it is every minute. When x is 0, it's known as the y-intercept. The y-intercept is also known as the initial condition, the starting point, when x is 0 and y is something. This initial condition is 82.933. This is what the temperature probe picked up at 0, the first point graphed on the graph. This is wrong. Because we put the temperature probe in the hot water and clicked start, it recorded the first temperature it felt. This makes it flawed. It didn't wait till it reached its maximum temperature before recording. So, as you can see, between 0, which is 82.933 degrees Celsius, and 1, which is 87.077 degrees Celsius, there is a rise in temperature, which normally would be wrong because as water left over time cools, not heats. But as the table continues, we see that it decreases in temperature. The decay rate, which is the same as the growth factor, only it doesn't grow, it shrinks. The decay rate is 0.97. This was found by taking minute 2 and dividing it by minute 1, which results in 0.97. Because I said that this initial condition is flawed, so I'm going to scratch it out. The real initial condition is 89.77. I found this by calculating it. This may not be exactly right, but is better than the initial condition given by the probe. I found this number by dividing the first minute, by 9.97. This was how I found the initial condition on this particular table. Here is the graph that matches the table. The orange plots are the actual recorded data from the calculator. The red line is what the Desmos app predicts when I put in the equation, which you will see on the next slide. As you can see here, in this graph, it is decreasing at a decreasing rate. The decay rate here is the same as on the table, found by dividing the second minute by the first minute. As you can see, the red line and the orange line are a little bit different. They start at the same point and look like they're going to continue together, but split. The reason they start together is because the numbers put in at 0 are the same. They start breaking apart because of the way my equation is formed. It is not 100% true to the data, because the data is not 100% exponential. It is very jumpy. Its temperatures, they don't fall at an even rate, as you'll see in my equation on the next slide. Here's my equation. Y equals 89.77, 0.97 to the power of x. Watch my laser and I will show a key points about this equation. Here is the initial condition, or the starting point, as I explained in previous slides. This 89.77 is when x is 0. The next point, which is here, is the decay rate. Same as the growth rate, only one shrinks and one grows. The decay rate is 0.97. And here is the power, to the power of x, meaning it can be put to any power. So you can put any number where x is, and it should find the point on the graph that matches the minute that the probe picked up. In the previous slide, we saw that the equation line does not match up completely with the probe line. That is because my equation is an exponential equation. It shrinks at exactly the same rate. But as we all know, in real life, it doesn't always look like this. It doesn't shrink at the same rate. When water cools, it cools not at an exponential rate, but it varies depending on the temperature in the room and who moves around it and gusts of wind. It does not cool at the exact same time. Most everything in the real world does not decay at a single rate, nor does it grow at a single rate. This is why Math World is awesome. Here's a summary of my learning. During this activity, I found out how to find the decay rate and how it's very similar to finding the growth factor. The only difference is one you will end up decreasing and one you will end up increasing. Thank you for watching. Hope you enjoyed.